Hello, and welcome to the Flotherm educational videos on troubleshooting models. There are 4 separate topics that I will go over in regards to troubleshooting Flotherm models. These topics are on convergence. We'll talk about some definitions, what the definition of the residual is, and then we'll give you examples of different convergence plots. Sanity check. We'll go over some common warnings and errors. Gridding deficiency. We'll talk about how to use the field error tool, the aspect ratio of grid cells, and whether or not you have enough grid cells in your model. And lastly, we'll talk about when and how to use the false time step in monitor point convergence. So let's talk about what convergence is and the different types of convergence plots you may encounter. When you start a Flotherm solve, this profile window will appear. In this window, on the left we have the residual versus iteration plot, and on the right we have the monitor points versus iteration plot, and that's only going to appear if you have monitor points set in your model. For the residual plot, we have a series of lines which represent pressure, x velocity, y velocity, z velocity, and temperature. On the y-axis, we have the residual, and on the x-axis, we have the iteration. Now, once these residuals go down all the way to 1 on the y-axis for residual, Flotherm will report the model is converged. Now, let's talk about what is a residual. A residual is a summation of errors in each of the grid cells of the Flotherm calculation. Flotherm solves the equations of mass, momentum, and energy. When the level of error becomes small, we can have confidence in our results. In essence, we are plotting how much error is left in the conservation equations versus iteration as we are solving. This is the ratio between the actual residual and the acceptable residual. When the actual residual equals the acceptable residual, that ratio becomes 1 and convergence is flagged. That is why the residual level 1 is at the bottom of the x-axis. Now, what is an acceptable residual? Acceptable residual is called the termination residual within Flotherm. By default, the value of this termination residual is 0.5% of the expected value for each conservation equation. Those numbers are derived from the defined model from power, fans, and fixed flows. Alright, so now let's take a look at some possible profile window scenarios you may see. In this case, our residual curves have decreased and reached 1. But if we look at our monitor points, they have not approached a horizontal line yet and are not in steady state. This means the Flotherm termination residual was not strict enough. In our next case, we have the opposite, where the residuals have not reached 1, but the monitor points are flat and in steady state. The default termination residual in this case is too strict. It is difficult for Flotherm to reach a residual of 1. And here we have an ideal case. Our residuals reached 1 and our monitor points are now flat and in steady state. This is what you want to see. Alright, now let's talk about some possible residual versus iteration scenarios. The first one on the top left is convergence. This is what we want to see. We start out with a high residual and eventually it gets smaller until it reaches the x-axis. Now, the opposite of that, on the bottom left we have divergence, where the residual error gets exponentially greater. This is bad. If you see this, there are a few things to review. Firstly, check your sanity check message window. Inspect the warnings and make sure you understand each one. Next, check all your inputs such as power, fan curves, or material properties. Make sure that's all properly done. After that, you want to double check and make sure you have some basic grid, not just your key point grid. And once you found your mistake, make sure to reinitialize and solve again. Don't just hit solve. Next, we have the oscillating residual on the top right there. This residual will bounce around at a certain level and never reach 1. This usually indicates some instability in the solver. This could either be a numerical instability, which we can address by adding more grid to capture the physics, or it could be the solver settings are too aggressive. It could also be that the flow field is a naturally unstable flow phenomenon, in which case Flotherm will never be able to give you a steady state solution. And lastly, on the bottom right, we have a flat line, where initially the solver has some progress, but then it flatlines and doesn't reach the x-axis. This can be caused by a permanent imbalance in the model setup, such as a heat source inside of an enclosure, and the enclosure itself did not have a material property attached. That heat will keep building up and have no place to go.